Okay, let's go ahead and get started today. This will be the last lecture. And again, even though we've already had part of the final, I think that this material can be important for you in your future. Next semester, you're going to be using this stuff throughout your career. You're going to be needing to understand some of this stuff. Graphics class, you may need to understand some of this. So this is going to be important for you going forward. And I'm sure you'll see some of this again. 100% sure you'll see it again in the data structures class next semester. So I would encourage you to watch these videos, watch these lectures, try to understand the stuff, and play around with it some. Also keep in mind that you have the last part of the final exam, the programming part of that next week. So some of this stuff might be on there. So important to maybe take a look at that. All right, so here's what we're going to do today. Is we're going to talk a little bit about C++ templates. And what templates are is they're a powerful tool for reusing code. For example, imagine a function that can change the data types of the parameters, or maybe even change the data type of what gets returned. Or imagine a class that can change data types as well. So for example, a list. Think of a list of items. And that list of items, you might want to have a program that makes a list of integers. You might want to have a program that makes a list of bullets for a game. You might want to have a list of inventory items. You might want to have a list of floating point values, a list of lists. And so the ability to have some kind of to write code that can adapt the data type based on how you want to use it can be really powerful. And in C, we don't have anything like that. In C, a function has to be written to work for a specific type and only those data types. For example, when you create a function in C, you have you give the function a parameter list and a return type, and the return type has to be something like int or float, or it could be a pointer of some sort, like a character pointer. It could be a structure, but in all of those cases, that return type has to be some sort of fixed type. It can't change. So if we want a function that has uses different types, we got to rewrite that function or write a different version of it. So if we want some sort of functionality to work with different types of data in C, then we have a couple choices. One choice would be to write completely different versions of the function, one version for each type that we want. We want to have linked lists of integers. We have to make the code that does linked lists of integers. You want to have code that does the average of an array of floating point numbers. We have to write that code to do that. We have to write that version. The other possibility is to use void pointers or pointers to structures that include a void pointer and some sort of type indicator, or use function pointers that point to a different function for different types, kind of like the qsort function in C does. But neither of those is really optimal, and they don't really make for readable or reliable code where we can make sure we're using the right types in the right places. So what we would like is to have some way to have the compiler still verify we're using the right types with the right kind of function, and be able to reuse code and have it kind of redefine itself for different types. Let's take a quick look at how that works here. So templates, think about common tasks like you want to sort things or search things or store data, make lists of data items, access those items in that list. Those are common things that we want to do, and that's the kind of thing we want to do with a lot of different types of data. Lists of bullets, lists of asteroids, lists of inventory items, lists of weapons that are available in the game, lists of players that are currently connected. So notice there's a whole lot of cases we want to do that, or sorting things, sorting student records, sorting the books in a library system, all kinds of cases where you'd want to sort things and put them in order. Lists of file names, lists of, so ability to sort things, but we want to have it be different types of things that we're sorting. And so we don't want to have to rewrite the same code for every different data type that we might ever encounter in our programming. We don't want to have a library for book sorting, routines and bullet sorting routines and student record sorting routines. We don't want to have to rewrite all those functions. So that's where templates come in. And if you've programmed any in Java, you may have seen generics. Templates in C++ are kind of like generics in Java. All right, so to implement templates in C++, there are two new keywords, template and type name. And really, type name, you can actually, there's an alternate for that, so you don't even really need to use that one. We'll see that here in a little bit. But template we are going to need to implement templates, which makes sense. All right, so let's take a look at a quick example, since that's what I think would make the most sense. So here's a template, and this is a function that we want to write that's going to give you the larger of two items. So in other words, you give two items to it. It could be like a student record and a student record. It could be an integer and an integer. It could be a float and a float. But we want it to return the bigger of those two things when we compare them. So we're going to templatize this function. So we write template, and then we use square bracket or angle braces, a type name. You could also put the word class here, which is why I said you don't need type name. So you can put the word class, which is what I usually do when I make templates. So template, type name or class, and then this T is kind of like, usually programs will use a capital letter like this, like single capital letter like that. But really, this is going to act now as our type that gets used through the rest of the definition of the function. So we're going to say there's this class T, type name T, and then T, everywhere we see it down here, is going to become the type of this function. So for example, imagine if we think of it like a pound define. Pound define T as an int, we would get int my max of 2, int A, int B, and then we would return the larger of those two integers down here. So notice that if I were to put a float there, then we would make a version of this function float my max of 2, float A, float B. So this T is kind of a placeholder for the type that's going to be used in the templatized version of that function when we go to use it. Now, how do we use it? Down here, you'll notice this C out thing is like kind of like how printf, a thing like printf is in C++. It's a way to, this is called a stream. And this left shift operator, what normally would be left shift operator, is basically that's a way of saying stuff whatever the output of this my max of 2 function is into that, and then stuff this in after that. So in other words, this end L is an end of line character. So this is basically saying whatever the output of this is, print that, and then print an end of line to go to the next line. You could have used printf down here because C++ is a superset of C. We could have used printf and a %d to print out what this outputs. We could have used a %f down here for this float. But notice here we are using that function, my max of 2. But notice after the name of the function, when we go to call it, we're going to put the type that we want it to be. So in other words, this thing in the angle braces down here, int, that's going to get plugged in for T, and it's going to compile a version of this function that has an int in all of the places where this capital T is down here. And it's going to make a version of that function, and it's going to call that version of the function and put a 10 and a 20 as what we pass to it. Now here's us using that same template, but now we're going to use a float version of that template. So it's going to compile another version of that function, the float version of it, that has float my max of 2, float A, comma, float B. And we pass the two floating point numbers to that. So the advantage here is we only had to write one function, but we could use it, the integer version of it, or the float version of it, and the compiler is going to handle creating those different versions for us and calling the right one when we use it based on what we put in the angle braces down here. And the cool thing about this is this would work with any type. I could have a character version of the function. I could have a pointer version of the function. I could have a version that works with other objects that we create, 2 rectangles, which rectangle is the bigger one, and our comparison code, as long as we did an overload of the kind of comparison operator, the greater than operator, then we could figure out which rectangle is bigger based on its area or something like that. So this allows us to create one function that can adapt to whatever type we want to use with it. Okay, classes can also be templatized. In other words, we can make templates for use in classes, and that's going to be important for us. So here's an example of that down here. Template class T, and again, class and type name are interchangeable. From here on out, I'll probably use class because that's what I do when I program. Notice it's a kind of different usage of this down here, but since we're specifying a type of something, you could either put type name or you could put class. Doesn't matter. It's in the C++ language spec. Both of them are valid neither one has any different functionality than the other one. All right, so here we're creating a template. The type that we're using is this capital T. So now inside of the class itself, I have two attributes, value1 and value2, that are going to take on that type. And then I'm making this, here's an inline function called item, or that's the constructor, that when I pass the two values in, they have that type. So imagine int. I can make an item pair that pairs two integers together. It's like think of it like a point. It has two values. It's a pair of integers. So here's the first one. Here's the second one. And value1 will take on the first, value2 will take on the second. And if I make that an integer pair, I'll have an int paired with another integer, like 10, 20. But I could also make a float pair and have a pair of floats. So I could make a pair of, I don't know, you have like, imagine a game where you have some sort of player object and you want to pair player 1 with player 2 to have them compete. You could use this item pair to have player 1 and have value 1 with a player object. So player value 1, player value 2, and you now have paired up two players with each other. And I could do that with this one single class without having to rewrite it. Okay, the ability of those templates to be used for classes, let's look at how we would actually use that. So to use that down here, we use item pair like a type. Classes can be used as a type. But then after the type name, temp or item pair, we have int. And this is making an integer version of this class. My pair 1, 2 integers. And then we can make a float version of that class, my pair 2. So notice they were both built from the same template, but we have an integer version of it, and we have a floating point version of it. We've created one of each of those. And now here, down here, we have that constructor being called, passing the two values in for pair 1, passing the two float values for pair 2. So now we have a class that can represent a pair of any two items as long as they have the same data type, as long as they're the same typed data item. Two integers, two floats, two players, two characters, two student records, two of anything that we want, as long as they have the same type, the way we wrote this. Now we could implement parts of that without inline functions as well. So back here, notice that we had this inline function for the constructor. Notice we could make other things. So here's an example where we have the inline function for the constructor, and here's a function that's declared elsewhere, t get larger item. So this is like the function prototype for this get larger item function that we have down here. And I need to fix a typo in here. Pair. Okay, there we go. So where is this get larger item method being declared? Well, it's declared down here, and since this is part of a templatized class, we also have to make a template for the method. So template class t, same thing we had up there, and now t is the return value, and item pair t, colon, get larger item. So notice that this is going to be the, if we make an integer version of this class, this is going to make an integer version of this method. If we make a floating point version of this class, this is going to make a floating point version of this method. If we made a player version of this class to have pairs of players, it's going to make a player version of that. All right, so very useful. The only thing that's sometimes confusing is when we write the method, we have to templatize the method if it's not an inline method up here. And the reason we don't have to do that up here is because this one is inside the class that's already has template t. This one, the implementation is not inside that class, even though it goes with that class. So we need to make it part of its own template, and the compiler will handle all of the generation of the code for us. All right, templates can also handle multiple types. So far, remember back with this one, we're making a pair of two like type things, an integer and another integer, or a float and another float. But over here, notice we could make a type of dissimilar, a templatized pair that can have two different things. We could pair a number with a float, or a number with a player, or a player with a number. And to do that, you'll notice that we can make a template that has multiple classes listed. So here's template class T1, class T2, and I've kind of highlighted these so you can see where they're being used. So T1 is going to be the type for value 1. T2 is going to be the type for value 2. And then here we are with the constructor saying T1 is the first, T2 is the second. So if we had an int and a float, those would get plugged in int value 1, float value 2. This would have the int for the first, the float for the second, and then we perform the assignment on those. And so, oops, hold on, where did I go? There. Okay, so now that class can support a pair of dissimilar items, kind of like a key value pair you would have in something like a dictionary, where you could say, this string I'm going to associate with this image object or something like this rectangle. So it gives us the ability to associate two dissimilar things. But notice we can templatize that even though there's two different types. And you can have more than two things in here. You could have any number of different types in your template. Now, one other thing you can do with templates is you can actually pass parameters in to that template as well. So for example, here I'm making a template. We're making like kind of like a dynamic array template here, an array template here. That's not dynamic right now, but an array template. And notice in this case, I'm going to say, well, when I make an array, I want it to have a type, and I want to know how many items there are, n. So we say template class T, comma, int n. So that, if that is another type, not the word class or type name. So if this is a thing like an int, then that becomes a parameter, and that n can get substituted in down here. So in other words, in this example, I have two functions that I create, or two methods for this. We can create it when we create one of these, and then we can do a set element, and we can do a get element. And notice that I use the same template down here that I used up there. The same things get plugged in down here, and the values get plugged in, and I can set the value at some particular spot, or get the value of an element at some spot. So take a look at that. Again, the highlighting on here is just for me to make it easier for you to see where those things are used. And one way you can kind of think about those templates is kind of like a pound define. Think about when you create a version of that function that would have like an int and a 100. Think about just cutting and pasting everywhere you see this T with int. And think about cutting and pasting everywhere you see this capital N with 100. So what's going to get created here is an int array of 100 items. And down here, void set element, we're going to pass to that this int value for what we want to set it to. And then when we get an element, it's going to return an integer that it finds at that position. And these are in here because the indexes are just like 0, 1, 2, 3, 4, and so forth. So these are just, those are indexes, not anything to do with that type, but because that's how indexes work. You can't have a fractional index. Okay, so templates with those default values, and notice here we are using that array. I left out the methods here, method implementation that we had over here just to make it visible. Notice if I say, well, let's back up for a second. Notice to use this, I could say my array, and then in square brackets I could say float 1,000. That would give me 1,000 floats. Now, you can also have default types and values that you assign to those things, to any of those in any template. So that means if it's not specified, then it'll use int as T and 100 as N. So you can specify those default things just like you with templates. So say if they don't specify the type name or the class, and they don't specify the size, in this case N, then we will default to using 100 or integers and 100 of them. Now, when we're using a class and we want to use the defaults, you can just do empty square brackets like that, my array, empty square brackets, because if we're not sending anything in, it'll just use the default types. But if we want to override that, so this empty is the same as if I said int and 100 like we have down here. But if I want to override that, I can and say, you know what, instead of 100 integers, let's make 1,000 floats. We could do that like we have down here. Okay, now, one of the best parts about these templates they're actually really powerful. I don't know if that came through or not, but hopefully it will after we talk about the STL for C++. So just like C language has this really rich library in the form of the standard library that has all kinds of things from like string manipulation to random numbers to the ability to do dynamic memory allocation. There's just tons and tons of things, file I/O things. There's tons of things that are in the standard library for C. But it turns out with C++, since it supports templates, that there's a standard template library that comes with all implementations of C++, where somebody's written code for us. And that code that they've written has this really rich library of templates for us to use. And they contain a whole lot of useful things like containers, and containers meaning like lists, sets, dictionaries, things that work like dictionaries. So if you're used to Python where you have like a list that's built into the language, it turns out the STL has a list for us to use. And in fact, there's a lot of versions of something that works like a list. And it's up to us. We can pick the one that most appropriately suits what we're doing. It's got iterators, which are ways of kind of moving through those containers or lists and sequences of things. It's got some algorithms in there for sorting and searching. It's got some functions in there that implement those algorithms that are templatized. And since all of those are templatized, the cool thing is we can use them with any type of data that we have that we want. So if we want a list of bullet types, we can do that. We want a list of other lists, we can do that. We want a list of inventory items, we can do that. We want a list of levels, and each level has inside of it kind of a dictionaries of key value pairs for settings and things like that, for difficulty and the number of enemies and the number of spawn points, whatever. You can do all of that with this thing that's already built for us with the standard template library. So that makes it really useful for most applications that you would ever want to do. So you don't have to worry about writing your own linked list code. You don't have to worry about implementing all that. We just use one of the containers that's made for us in the STL, and because it's templatized, we can use it for whatever our problem happens to be. And that's really one of the best things about the existence of templates and the STL is because it's going to make a lot of our code easier because we're not going to have to write a lot of that. It's already done for us, and it's done in an efficient way and a very complete way. Okay, so let's take a look at some of the container templates that C++ has in the STL. So pair. We wrote our own little version of a pair earlier, but C++ has built in a pair, a vector. And vector here, you might think of it like a vector 3. It's got 3 parts to it. But a vector in the STL is really like a dynamic array in C. You can have it be any number of items stored in like a list. So think of it kind of like a tuple or a list if you're used to Python. But the advantage of it, the way that it's set up, is rather than being like a linked list where you've got to jump through each of the nodes to go through them, you can index it just like an array. So it's very much like a dynamic array, but it's been done for us, and it can be an array of any type we want because it's templatized. Now, it also has doubly and singly linked lists that are stored as linked lists. There's this thing called a DQ or double-ended queue. Some people, I've heard them pronounce this DEC, but I think it's DQ or double-ended queue. But that is kind of like a list, but you can access both ends. So you can push things on the front, or put things on the front, insert things on the front, pull things off the back. So it's kind of like very useful for buffers where you need to have inserting things on one end, pulling things out of the other end. So it's useful for things like a buffer. There are also things called sets where there's no real order associated with it, but you can insert things into the set. You can check to see if things are in a set. And with a set, there aren't any duplicates. So if you add something to a set that already has it, it'll just ignore that. The set will stay the same. There's also a multi-set that you can add things, and it allows duplicates. There's a map, which is a lot like a dictionary with key value pairs. And there's a multi-map that allows duplicate key. It's key value pairs, but you can have duplicate keys in it. And all of those are really useful. Think about the kinds of things you've done in Python. You make lists of objects. Well, we can do that with a vector or a list or an S list or even a double-ended queue. You have a set of things. There's no real set in Python that's built in, but in C++ and the STL, there's one that's in there. So we don't have to worry about having duplicates. Also, things like dictionaries in Python. Well, that's what a map is like in the STL in C++. So most common programming tasks that you'd come across, and really a lot of uncommon ones, you can do with one of these versions. And notice that since there's multiple ways of doing it, the most common ones that I would say you'd end up using would be vector and map. And maybe you would use lists to some extent, but you can do everything with a list that you can do with a vector. Vectors are a little more efficient in some ways. Accessing them can be more efficient. But removing items from a vector, just like a dynamic array, it takes longer, because to remove something from the middle of that vector, you've got to collapse everything else down, where lists, you can just unallocate something and throw it away. But these are all really useful to learn. The ones I've used most often: vector, list sometimes, double-ended queue, and map, with the strongest usage of map and vector, especially vector. All right, let's look at a quick example of how you would use the standard template library. So here's an example. Notice to use, for example, vectors. This is going to use vector. To use vector, we just say #include vector. You do not put a .h on there. In the C++, the standard template library things, you don't put the .h. You just say vector. So we're going to say, hey, use the standard vector. Now, once we have that, it's loaded up into the standard namespace, because this is the standard template library. So we say standard std : vector. And since we included that, we can use that. And then since it's templatized, we're going to say, hey, make a vector of type int and call it a. So we're making kind of like this array that right now has nothing in it, and we're calling it a. Now, after I've created that, I can put things into that vector by using pushback puts things on the end of the vector. So in other words, we're saying when it first gets created, it's empty. It's like an empty list. So this would be the equivalent of something in Python like saying create an empty list. And then this would be the equivalent of saying append in Python, a.append. But in C++ and the STL, it's called pushback, which says push something on the back of this vector, put the number 1 on the end of the list. And then after that, put the number 2 on the end of that, put the number 3. And now this thing here, this standard : vector int, this const iterator, that's an iterator. And what an iterator is, it's kind of like, you can think of it like a pointer that points at that object. And then when we increment it, it moves to the next one. And when we increment it again, it moves to the next one. But the advantage of using an iterator here is that you can use an iterator not just on pointers like in C where you have pointer arithmetic, but you could use it on something like a linked list where it'll automatically go to the next item for us. So the iterator here, a.begin is the beginning of the list. A.end is the end of that, or in this case vector, the end of that vector. So what we're doing is we're saying, hey, start the iterator at the beginning, and while that iterator is not at the end, increment it. And what are we going to do each time? Here I went ahead and used printf instead of cout, but we're going to print out that integer that's at that position. So thing pointed to by the iterator gives us that object that's at that position. In this case, it's an integer because we have an integer template. So this is just going to print 1, and then a space, and then a 2, and a space, and a 3. And then at that point, we will have reached the end of that array A, and this loop will stop. So this gives a really simple example that you can use. There's also a way where you don't have to specify this std : every time when you're accessing these. And that is, you can say using std, which says basically use the standard thing. So that using kind of sets the namespace that you're using. But you got to be careful with that, because if you have things in that namespace that overlap with local variables or other things that you're accessing, it's similar to Python. It's kind of like import something from rather than just import that. But so I usually prefer to leave these because it makes it clear this vector is coming from the standard namespace here that this imports things into. All right, a couple, since we used vector over here, let's look at a couple of the other methods and elements that it has available to it. So the cool thing about vectors, we can access them or index them just like we would arrays. But a.begin, that gives us the iterator to the first element. This a.end is kind of the iterator to the end, at the end element. A.at returns the iterator at a specified index. A.front gives us the first element. A.back gives us the last element. So front and back, notice those are different than begin and end. Begin and end give us an iterator. Front and back give us the actual element that's at that first position, and element that's at the last position. And again, think of the iterator kind of like a pointer in C, that a.begin is saying, give me the address of the beginning element, where a.front is saying, give me the thing pointed to by there, give me the beginning element. And those are different things. A.empty returns true or false. True if the thing is empty, false if it has stuff in it. A.size returns the number of elements that are in that vector. Again, this is kind of like the length of a list in Python if you're used to that. A.clear erases everything out of the vector, so you can put things in, clear all of them out. A.insert, we use an iterator and a value. It'll insert something at that position. And if you want to use something like an index position for where you want something inserted, you could say A.begin plus and then some number. And again, think of those iterators as kind of like pointer arithmetic. So we plus 0, we're at the beginning, plus 1, we're in the first element's position, and so forth. But this lets us insert items anywhere we want into that list or into that vector. Push back we've already used. That actually sticks an item at the end of the list, just like append in Python. And then pop back removes and returns the last element on the back of that thing. And you can do a.erase, give it 2 iterators. In other words, delete a range of things out of the middle of that array if you want to. All right, so keep in mind that one of the nice things about the STL is you can use the template with any type, and that includes user-defined types. So if you wanted to make a vector of bullet objects, you can do that. You want to make a vector of really anything, a vector of player objects, you can do that. You want to make a vector of asteroid objects or enemy objects or spawn points or health boxes or inventory items, you can do that. STL has you covered with all of those things. So let's look at some full STL example programs, and we're going to look at ones that use both a vector and then another one that uses a list. So what I'm going to do is I'm going to go ahead and switch to the code so you can actually see that code here. So let me actually bring that up in a code editor here. Okay, so let's look at the list example first. So this is a list, and the list in the STL essentially is using a singly linked list, which means that accessing items can be slow because it's got to start at the beginning and index through all of them to get there. Slower than with a vector, which is why I'll use vectors more often than that. But if we're inserting items a lot or deleting items a lot out of the middle, it turns out the list is faster for those kinds of things than a vector. Okay, so a couple quick things here. I designed this code or wrote this code to be very similar to the stuff that we had done previously with linked lists and dynamic arrays in C. But this is using vector or using lists for that. We're going to see the vector version in a second. So notice here I have #include list. I also #include this IO stream thing because I'm using cout down here to display those, and those things are part of that. And notice that here I'm using namespace standard, so I don't have to type that in with a ::" every time I want to use one of those things. So this is us, the list example. So down here, list, and I'm making a list of integers, int list. Here's my array. I'm just going to go and push them all on the back. So this is pushing them all on the end of my list that I created. So I'm going to get all of these items here pushed onto the end of that list. And now I'm going to call my print list function, which I'm going to show you the implementation of that in a second. And then after that, I'm going to remove the item that's at index 1 by calling my delete item at index function on that list. And then I'm going to do a print list again. And then I'm going to clear the whole list by calling my delete list function. And then I'm going to print list one last time, and then I'm going to be done. All right, so let's look at the implementations of those. And the implementations of those functions, noticed list int. I made that an int type to match this type up here that we made that. And that ampersand there, remember, that's a pass by reference. And then inside of this, I make a list iterator, and then I iterate through to print all of them one at a time, printing out the value, colon, and then the thing that's at, or the index number, and then what's at that, and then an end out. So I'm going to get a whole list of all those things printed out one after the other. And then I have this delete item at index that basically just does a v.erase, which erases the entire list. And then down here to delete list, I just call clear to do that. So notice to delete something, we go to the beginning. I'm advancing ahead by this number of positions into that iterator. And then advance, it says go to the next, essentially is a way to say go to the next item. But you can pass an index, say how many places ahead you want to advance in the linked list. And then I erase the item that's at that location, which takes that node out, puts the list around it, does that. So this is, look at this side by side with the dynamic array example and the linked list example we did ourselves. And notice that we didn't have to write a lot of the code. It's already done for us. It's in the STL handles pushback. It handles the stuff to create the class itself. It handles figuring out where the beginning is, where the end is. It figures out how to advance the pointer to that linked list to whichever item we want, and how to erase an item, a node that's in that list, and how to clear the entire list. It's all built into it. So all I did is make some functions that kind of wrap around the functions that already existed for me. All right, so that's the STL list example, and I will post a zip file of these to the course page so you guys can download them and take a look at them. Now let's look at doing the same example, but let's do it with a vector. So here it is with a vector, and I made two versions of print list here that worked in different ways because print list has to iterate through all of the items in the list. But notice that this works the same way. I just have vector here instead of list. I include vector instead of list. And then I do push back to put things on the end of it, just like before. Print list, I call print list, I call that. Here I call print list 2 instead of print list 1. But let's look at the how each of these works. So again, to delete the list, I just call v.clear, clear the vector. To erase an item at a particular spot on that, I say v.begin plus index, v.erase, that erases an item, which will collapse everything down for me. Again, it's all done formulous. It's one line of code to do all of this. It would have been a lot of work if we had to make the linked list or dynamic array ourselves. And then here, for print list, let's compare and contrast the two versions that I created. The first one uses an iterator to go through the vector. Again, starts at the beginning, goes till while we're not at the end, increments the iterator. Also, I have this I index in here just for printing it out. So you can say, here's index 0, here's index 1, here's index 2, and so forth. So when I do the thing pointed to by that iterator, I get the value that's at that position. And then this does the same thing, but it's using indexing, kind of the square bracket traditional array indexing down here, rather than using an iterator like we are up here. So there's two ways of doing that. Now, this square bracket notation will not work on lists, though, or doubly linked lists. So it won't work on lists, won't work on d-lists, but it will work on vectors, and that's because a vector is kind of like a dynamic array. It's all contiguous memory. So notice we can do that and index into whichever element we want. All right, so I'll post those examples to the thing, but notice very little code, but we have this list. And notice how easy it would be to change this to be a vector of some other type. You wanted a bullet vector, make a bullet class, put bullet there. You want some sort of a vector or a list of floating point values instead of integers, just put the word float there. Push floats into it. So very much like a good way to think about this is kind of like lists in Python, but much faster because it's C, C++. I know I have C up here in the comment. I should probably change it to say C++ and save these off. And I'll make a zip file of those and I'll post them to the course page. All right, let's go back to the presentation just briefly here. So let me switch over to that so you can see that. Okay, so we looked at those examples, and the thing to note there is how easy that is compared to having to write our own dynamic arrays or linked lists in C. STL did the difficult work for us. All we had to do was use the stuff that was already created for us. That's all for now, and really that's all forever for this class anyway. I hope everybody learned something this semester. I know there were some struggles with the remote delivery method of how things were done. I know people got, things are just different now because of COVID, and it made, I'd much prefer to be in the classroom with you guys, standing at a whiteboard, doing that stuff. But the thing I want is, I hope everybody to learn something, and I want you guys to realize that C and C++ are great languages and are kind of foundational if you want to be a wizard, rock star, fantastic, competent programmer. And I'm serious about that. If you are good at C and you're good at C++, then you can get jobs that pay a lot of money, and but you need to understand how those languages work. If you're a rock star C programmer, hell, I would hire you for my business today. There's a strong need for good, competent programmers that know C and C++. And C and C++ are really how all the other programming languages are built on top of that. For example, Python, the Python interpreter is written in C, the one that most people use. The Java virtual machine is written in C. The Windows operating system, C and C++ is how most of it's written. Linux, C. The Linux kernel, C. Linux outside of that, C and C++. Mac OS X, C. Android, C. All of those languages are written in C and C++ for a reason, and it's because it performs well and that they're great languages that you can do a lot in. They're also, they have a reputation for being difficult to learn. I do think C++ has some parts that are weird and that doesn't quite make sense. It's a little more verbose than it needs to be. C, since it's so low level, requires you to do a lot of work, but I don't think it's as hard once you get used to it as a lot of people make it out to be. And using the STL in C++ simplifies a lot of common tasks for you. And so it'd be useful to learn about that as much as you can if you're going to be a good C++ programmer. All right, one final thing. Don't forget about the programming part of the final. That will be next week, finals week. And make sure you don't blow that off. Be prepared for that. Best way to prepare for that, learn all the stuff, look at all the lectures, make sure you've done all the labs and you understand what you've done. And other than that, stay safe, and hopefully I'll see you guys next semester. And hopefully you guys have a good Christmas break and things get back to normal sometime next year. And then we can actually have a class together where I get to stand in front of you at the whiteboard and we get to joke around and talk, and you can make fun of me and I can make fun of you, and you can heckle me and I can shoot you down. But don't forget about the programming part of the final. That's worth 20 points, and there's a chance for bonus points on there on the final too. So if you didn't do so well on the paper part, knock the programming part out of the park and get some bonus points, and you'll be doing good. All right, that's it. Everybody stay safe, wear a mask when you're out, and if everybody does what they're supposed to do, then maybe we can see each other in the classroom sometime soon. Have a good break. Bye.